Okay, so this is a discussion for experiment 23. It says experiment 22 there, but it's actually experiment 23. And this experiment has a goal of determining the formula of a complex ion. So we want to determine the formula of a complex ion. So complex ions are composed of metal cations and ligands. So that's what we're going to mix together. We're going to mix together the iron 2 cation, and we're going to mix together some amount, I'm going to call it Y, of phenanthrene molecules. And I'm going to talk about the structure of that in just a second. And that's also an aqueous solution. And so we're going to get a complex ion that is composed of our iron 2 and Y number of phenanthrenes. And that's a neutral molecule, so the complex ion has a charge of 2+. So both the iron 2 and the phenanthrene is colorless. Both of those are colorless solutions. And the complex ion is a red-orange solution. So since our product is red-orange, and this is a product-favored reaction, so we're going to see red-orange, we can use absorption spectroscopy. So now I'm going to go ahead and talk more about this phenanthrene molecule, which acts as the ligand in this experiment. Okay, so this is the phenanthrene molecule right here, and iron 2. So I just wanted to talk a little bit about this molecule. And so I'm going to draw a couple of electrons on there. Okay, so there's a lone pair on each of these nitrogens. Okay, and it's a big molecule. So that essentially means that this molecule can be bidentate. It can bind twice. This lone pair on nitrogen can form a bond with the iron 2, and this lone pair on nitrogen can form a bond with the iron 2. So I'm actually going to show the bonds here. So let's make a bond between, we want to make it between our iron and our nitrogen. So once I do that, the lone pairs I'm going to erase because they're gone, right? They went to form the bond between the metal cation and the ligand. Okay, so it's a bidentate ligand. Binds twice. So bidentate, it binds twice to the central metal cation. On the right here we just have the ligand, the three-dimensional structure, so you can see it, right? And you can rotate it around. In Canvas, I have this embedded if you wanted to take a look at it, but there's our two blue nitrogens, and those are the ones that are forming the bond to the central metal cation. All right, so that's the ligand. And I can go ahead and show in the 3D model what it looks like when we have iron bonded, the iron cation bonded to the phenanthrene. Okay, so here's our iron, and it's bonded twice bidentate. And again, I can rotate this around. So our job is to figure out how many of these phenanthrene molecules bond to the central metal cation, iron 2, and then from that, get the coordination number. So to do this, to figure out the formula of the complex ion, we're going to use the Jobs method. I don't know if it's Jobs or Jobs. I'll call it the Jobs method. And so I'm going to explain this method by looking at the solutions we're going to make. We're going to make 12 solutions labeled tubes 1 through tubes 12. And in there, we're going to put our cation, iron 2, and our ligand, phenanthrene. Okay, so in tube 1, we are going to put an excess amount of iron. So we have an excess amount of iron in tube 2, and we gradually decrease it, where by tube 12, it's the limiting reactant. And it's going to be the opposite for the phenanthrene ligand. We're going to start in tube 1 with a limited amount. It's going to be the limiting reactant, but at the end, it's going to be excess in tube 12. So somewhere in there in tubes 1 through 12, we have the perfect amount. So I don't know which tube it's going to be. We'll have to watch the video and look at the data. It is going to have the perfect amount of both iron 2 ion and phenanthrene to produce the maximum amount of product. Right? We're not going to run out of phenanthrenes. We're not going to run out of iron. We're going to produce the maximum amount of product. And this tube that produces the maximum amount of product is going to be the darkest red-orange tube in our set, right? So we have 12 tubes. The darkest one means we produce the most amount of the complex ion product. And if it has the darkest color, it's going to have the highest absorbance value, right? We're going to record the absorbance of our solution, and the one that's the darkest will have the highest absorbance value. So what we're going to do is take the absorbance values and the concentration, not in molarity, in mole fraction, to make what's called a jobs plot. So our jobs plot has the absorbance on the y-axis and concentration on the x-axis like we're used to, but in this case it's a mole fraction of the ligand, which is the moles of the ligand divided by the moles of the ligand plus the moles of the metal cation, which in this case is iron 2. So once we take our data, we're going to record the absorbance of the red-orange solution. And we are going to see first that we are increasing in absorbance values for those 12 tubes. We're going to start increasing, which is my white line. But then we're going to see where we have a maximum value, and then it starts to decrease. So I'm going to draw another line that shows the decreasing in the absorbance values as a function of those mole the mole fraction of the ligand, right? And so essentially those two lines intersect. So I'm going to draw the intersection point, and we're going to talk about what these lines mean. Okay, so those two lines intersect. So the white line, that is when in our tubes when we have a limited amount of the ligand, the phenanthrene, right? I mentioned how we start out with a limited amount of ligand. So the amount of product we get is limited by the phenanthrene ligand, the amount that we put into the tube, right? But then we get to a maximum value, right? We're going to get to that sweet spot where we can make the maximum amount of product. And then we get values that are going to start to decrease because that's the yellow line. In the yellow line, we are limited by now the iron 2 plus. So we can't make as much product because we're limited by the amount of iron 2 in the tube, right? But there's that sweet spot where we make the maximum amount of product. And if we intersect the two lines, and we can, if we have equations of both of the lines, we can solve for the x-axis, the value at the x-axis where we have the intersection. And that is our maximum amount of product right there, right? That's our maximum absorbance. It's the maximum amount of product produced. So that I'm pointing an orange arrow to where we have the maximum amount of product produced. So we have that sweet spot where we've added the perfect amount of the ligand, the perfect amount of the iron cation. And so again, you can solve for what point that is on the x-axis, right? And so I'm going to do an example. Your data is going to show you something different. But let's say I solve for that intersection point by setting the equations of the lines equal to each other. And I said that that point is equal to 0.50, right? So I'm going to draw a dashed line down here to the x-axis, and I'm going to label that as 0.50. Okay, so we have to solve for this algebraically, which you will. This is just an example. So that 0.50 is equal to the mole fraction of the ligand. Okay, so that equals 0.50, the mole fraction of the ligand. And the 0.50 equals the moles of ligand. I'm going to call it Y. So we have Y moles of our phenanthrene ligand divided by Y moles of the ligand. Plus, we know it has to be just 1 mole of iron, right? So at every mole of compound, I just have 1 iron in the center. So I know those moles of iron is 1. So Y moles over Y moles plus 1 mole is equal to 0.5. So you might be able to solve for that in your head, but we'll do it algebraically. So I'm going to multiply each side by Y mole plus 1 mole. So I get Y equals 0.50 times Y plus 1, right? And I left off the units. The units are mole. So I'm going to move up over here to the right top of the screen to solve for this. So I am going to multiply the 0.5 through. So I have y equals 0.50 times y plus 0.5, or 0.50. Solving for y, I want to subtract 0.50y from each side. So 1y minus 0.50y gives me 0.50y equals 0.50. Dividing each side by 0.50 tells us that y equals 1. Right, I have 1 mole of ligand divided by 1 mole of ligand plus 1 mole of iron, 1/2. So 1 divided by 2, 1/2. So what we can say is that the formula of our complex ion for this example would be iron with 1 phenanthrene, and it has the 2+ charge. And we could say then that the coordination number equals 2. Since phenanthrene is a bidentate ligand, if I have one of them, there's 2 total bonds to the central metal cation. So that's kind of like the model I showed you previously, just attaching one of the phenanthrenes to the iron 2. All right, that's not what you're going to get for your data. You're going to get something else, but I just wanted to show you an example of how the math works out. All right, so that's how you're going to get your formula. Solving for the x-axis where the lines intersect, which gives you the mole fraction of the ligand. We know that there's always just 1 mole of our central metal cation in our formula, so we can solve for the moles of ligands. So in order to do the Chobs plot, you need to determine the mole fraction, right, of the ligand. So you have to use the given information to determine that. So given to you is the concentration or molarity of the iron solution and the phenanthrene solution, as well as the volumes used to make the 12 different solutions that you're going to measure. So that's what's given to you. So let's think about what the concentration is and what the formula is. So mole fraction of the ligand is equal to the molarity of the ligand times the volume of the ligand to give us moles. And then we divide it by the molarity of the ligand times the volume of the ligand, plus then the molarity of the iron 2 times the volume of the iron. Oh, that should be times the volume of the iron 2. Right, so that's multiplied, right? Molarity times volume gives us moles. So molarity of the ligand equals the molarity of the iron 2. They're both 3.00 times 10 to the negative 4 molar. So they're equal to each other. So molarity, I'm just going to use now M. So I have molarity times volume of the ligand, and I have molarity times the volume of the ligand plus the volume of the iron solution, the iron 2 solution. Right? I can simplify that. I can pull that molarity out. So the molarity essentially cancels out, and we can just take the volume of the ligand divided by the volume of the ligand plus the volume of iron. Right? That's a shortcut. I don't have to calculate moles. We can, because the concentration's the same, it cancels out. So essentially, we just need the mils of the ligand divided by the mils of the total volume. Right? And the total volume in every tube is 5 mils. So this is a little shortcut. You can take the volume of the ligand divided by the volume, the total volume, and that will give you mole fraction since the concentration of the ligand equals the concentration of the iron solution in this case. So to summarize everything I've talked about, you are going to watch the video to get the absorbance data from the video. Okay. You need to make a Jobs plot with that data and with your calculated mole fractions. And you can make that Jobs plot in Excel in the experimental procedure. It describes how to do that. Or Google Sheets. If you don't have Excel, the video shows you how to do this type of plot in Google Sheets. Make sure you have a descriptive title, not just absorbance versus mole fraction. Okay, it needs, I don't want verses in your title. Make sure you label the axes. Then, of course, you need to determine the formula for the complex ion, right? So you have that iron with Y number of the phenanthrene ligands. So you're trying to determine what Y is. Okay, to summarize how to do that, right, you are going to solve for the intersection point of the two lines in the jobs plot. And so you want to solve for the x-axis where they intersect, the x value where they intersect. And so that's, again, the x, and that is the mole fraction of the ligands. So that's our x value. X represents mole fractions of ligands. And your mole fraction of ligand is equal to y divided by y plus 1. So you'll have the mole fraction of ligands. You can solve for y, which gives you then the value in your formula.